Before we install anything, I want to spend 5 minutes on where this language came from. Not because history is decoration, but because almost every design decision in Kaappi is an answer to a question somebody asked decades ago. If you know the questions, the language stops looking strange and starts looking inevitable. 1958. At MIT, John McCarthy is trying to write a language for artificial intelligence research, something that can reason about symbols rather than just crunch numbers. What he designs is called Lisp, for list processing. It is the second oldest programming language still in use. Only Fortran is older, but the idea underneath it is older still. In 1936, the logician Alonzo Church described a system where absolutely everything is a function, where you can compute anything at all using nothing but functions that take functions and return functions. That system is the lambda calculus, and it is the bedrock the whole family is built on. Lisp's one big structural idea is almost embarrassingly small. You get a box with 2 slots. Put a value in the first and a pointer to the next box in the second. Chain those together and you have a list. Chain them differently and you have a tree. Every data structure in the language grows out of that single 2-slot box. And here is the consequence that makes this family different from everything else. Programs are written using those same lists. Your code has exactly the same shape as your data, which means a program can read, build, and transform other programs as easily as it sorts a shopping list. Most languages bolt that on later and call it reflection, which leads to a party trick that turns out to be a deep truth. You can write an interpreter for Lisp in about a page. The language is small enough and regular enough to explain itself completely in terms of itself. Nobody has ever really improved on that as a way of teaching what evaluation actually is. By the 1970s, Lisp had spread and splintered. Every lab had its own dialect, each one accumulating features, each one slightly incompatible with the others. The language that was famous for being tiny had grown into a family of large, sprawling cousins that could not quite talk to each other. 1975. Guy Steele and Gerald Sussman at the MIT AI lab go the other way. Instead of adding features, they strip the language back to see how little they can get away with. The result is Scheme, and its governing principle is stated right there in the report. A language should not pile up features. It should remove the weaknesses that made them seem necessary. Scheme got 2 things very right, and the first is closures. When you make a function, it carries its surroundings along with it. The variables it could see when it was created stay visible to it forever, wherever it ends up being called. It is a lantern, not a torch on the wall. That one property is what makes functional programming actually practical. The second is proper tail calls. In most languages, a function calling itself over and over eventually exhausts the stack and crashes. Scheme requires that when a call is the very last thing a function does, it reuses the same frame instead of stacking a new one. So recursion becomes a loop, mechanically, and you can write a million iterations as a recursive function without a care. And then there is the one Scheme is notorious for. Call with current continuation lets you take the entire rest of your program, everything that would happen next, and grab it as an ordinary value you can hold, pass around, and jump back into later. Exceptions, generators, coroutines, backtracking, they are all just this one thing wearing different clothes. Scheme is standardized in a series of documents with a wonderful name, the revised reports. Revised, then revised, and so on, which is why you see R5RS, R6RS, R7RS. And the small language they describe is genuinely small. You can read the whole specification in an afternoon, which is not something you can say about most languages you use. That smallness made it the teaching language. Structure and Interpretation of Computer Programs came out in 1985, used Scheme throughout, and taught a whole generation of programmers to think about abstraction rather than syntax. If you have ever heard someone say, a language changed how they think, there is a decent chance this is the one. So why isn't everyone writing Scheme? Because elegance on paper and speed on real hardware have historically been 2 different projects. Beautiful semantics are one thing. A garbage collector, a bytecode machine, and a native compiler that make them fast are quite another. That gap is where most small language implementations quietly stop. Which brings us to the tool this one is built with. Zig is a systems language with no hidden allocations, no hidden control flow, and no runtime of its own to fight. You see exactly what the machine will do. For writing an interpreter, where every allocation and every branch is in the hot path, that kind of directness is worth a great deal. And that is Kaappi, a complete R7RS small scheme, written in Zig, named after the Tamil word for coffee, which is why our mascot is a pour-over cone. Everything the reports ask for: closures, proper tail calls, full continuations, hygienic macros, the numeric tower. All of it, in one small binary you can install in a second. And it does not stop at interpreting. The same source file can go through LLVM and come out the other side as a genuine native executable. No interpreter needed. No runtime to ship alongside it. You write the lambda. The machine runs the metal. We will do exactly that, on camera, in about 15 minutes. So that is nearly 70 years from a blackboard at MIT to a binary on your laptop. Hat off. That is the end of the history. Let's go and look at the actual thing. So here it is, in the present tense, kaappi-lang.org. Everything the cone just walked you through, 1958, 1975, closures, tail calls, arrives here as something you can download in one line. Write the lambda, run on the metal. Let's look around before we install anything. And the front page doesn't waste your time. There's the language, in one line. Map a lambda that squares x over the numbers 1 to 5, and get back 1, 4, 9, 16, 25. If that expression makes sense to you, you already know how to read Scheme. If it doesn't yet, it will in about 10 minutes. There are really only two doors here, and I'd take them in this order. One installs it on your machine. The other runs it in the tab you already have open, with nothing to install at all. We'll do both, and we'll do the free one first, because there's no reason to make you commit to anything yet. This is the install page, and this is the whole install. Curl the script, pipe it to bash, and you get two binaries: Kaappi itself and Thotum, the package manager, plus the standard library. We are going to run this exact line, unedited, on this exact machine in a few minutes, so you'll see precisely what it does. And if piping a script into your shell makes you uneasy, reasonable, the same page has signed binaries for macOS, Linux, Windows, and the BSDs, with the checksums to verify them. But first, the door that costs you nothing. This is a real playground, not a video of one, and not a server somewhere running your code for you. It is Kaappi itself, compiled to WebAssembly, running inside your browser. So let's ask it something a calculator would get wrong. A third plus a sixth. Not 0.5, and not 0.4999. Exactly 1/2. Kept as a fraction the whole way through. That is the numeric tower doing its job, and it's running in a browser tab. That is about as low as the barrier to trying a language gets. And one more, because it makes a point about the history we just covered. Factorial of 30, defined recursively in one line. 33 digits, and no overflow anywhere. Integers here grow to whatever size the answer needs. In most languages, that returns a wrong number, silently. Have a play with this page while you listen to the rest. It's the best possible companion to what comes next. If you'd rather be led through it than poke at it, there's a tour. 12 short lessons with a live editor next to the bros. Hello world, numbers, strings, lists, defining your own functions, and onward. You read a paragraph, you change the code beside it, you run it, and the next lesson assumes you did. It is the fastest structured path into the language. When you want depth rather than a tour, the guide is the manual. Installation and a first program at the top, then the language itself, then the working parts, the REPL, the command line tools, the debugger, editor setup. Further down it gets serious. Concurrency, writing your own extensions in C or in Zig, security, and deployment. Procedures is the reference. Every built-in, grouped by what it operates on. Numbers, pairs, and lists, strings, characters, vectors, byte vectors, ports, control flow. And then the SRFIs. Those are Scheme's community standards, the library layer on top of the core language, and Kaappi ships more than 170 of them. SRFI 1 for lists, 13 for strings, 133 for vectors, hash tables, threads, and a great deal more. When you're mid-expression and can't remember an argument order, this is the page you want open. The cookbook is shaped the other way round. The thing you're trying to do rather than the function you'd use. Build a REST API. Talk to one. Read a CSV. Query SQLite. Write a config file. Run some tests. Put together a command line tool. If you learn better by starting from a working program and bending it, start here rather than in the reference. And a language is only as useful as what ships around it. Around 20 libraries: JSON, CSV, TOML, and YAML for data, sockets, HTTP, email, and Redis for the network, PostgreSQL and SQLite for storage, a test framework, a BDD framework, logging, templates, a computer algebra system, and a web framework on top. The dependency graph shows how they stack, and every one of them installs with Thotum. There's an FAQ for the questions you're probably already forming. How this compares to the other schemes, what's actually production ready, how fast it is, and what happens when you hit something it doesn't do yet. It's worth 2 minutes before you invest an afternoon. So that's the map. A playground to try it, a tour to learn it, a guide and a reference to work from, a cookbook for recipes, and an ecosystem for the rest. Every link is in the description. But reading about a language is not the same as having one, so let's stop browsing and put it on this machine. For real, right now. Right. Enough history. Installing it is genuinely one line. Curl the install script from kaappi-lang.org and pipe it into bash. It works out which machine you're on, fetches the matching release, verifies the checksum, and puts the binary in your local bin directory along with the standard library. No package manager, no build step, no dependencies to chase. And that's it. Kaappi version 0.22.0 sitting on your path. If you're on Linux or one of the BSDs, that exact same line works there too. Type Kaappi with no arguments, and you get a prompt. This is the read eval print loop, the REPL, and it is where you should spend your first hour with any Lisp. Type an expression, press enter, get a value back. 2 plus 3 is 5. 6 times 7 is 42. The only thing that looks odd is that the operator comes first, inside the parentheses. Plus is just a function, and calling a function means putting it at the front of a list. That single rule is essentially the whole syntax. There's one small convenience worth knowing on day one. The underscore holds whatever the last result was. So 2 plus 3 is 5. And then underscore times 20 is 100. When you're exploring, and exploring is what this prompt is for, it saves you naming things you're only going to use once. Here is the expression this project puts on its posters. Lambda makes a function without giving it a name. This one takes an x and multiplies it by itself. Map applies that function to every element of a list and hands back the results. 1, 4, 9, 16, 25. No loop counter, no accumulator, no mutation. You describe the transformation, and the list comes back transformed. Now, something that catches people out pleasantly. 1 divided by 3 is not 0.333 repeating. It is 1/3 held exactly as a fraction. Add a third and a sixth, and you get exactly a half. Scheme has what is called a numeric tower. Integers, rationals, reals, and complex numbers. And it stays exact for as long as it possibly can. Which matters, because the moment you write decimals, you are back in floating point, with all its usual sharp edges. 0.1 plus 0.2 is famously not 0.3, here as everywhere else. The difference is that Scheme makes the choice explicit. Exact is the default. You opt in to approximation, and the function you call to do it is honestly named. And integers simply grow as large as they need to. 2 to the 100th power is not an overflow. And it is not a special library you had to import. It is just the answer. 31 digits of it. You never have to think about the width of an integer again. Anything starting with a comma is a command to the REPL itself, rather than Scheme to evaluate. Comma time evaluates an expression and tells you how long it took. Here, 2 to the 1000th power, 302 digits, in a time it declines to distinguish from 0. And comma describe tells you about any name in scope, what kind of thing it is, and how many arguments it takes. There are about 20 of these commands. Comma help lists them all. Between describe, apropos, and the built-in debugger, you can answer most questions about a running program without leaving the prompt. Let's build something up. Define gives a name to a value, and when you write it in this shape, it defines a function, square, taking an x, returning x times x. Call it, and you get 144. That is the entire declaration syntax of the language. There is no separate type signature, no return keyword, no braces. The last expression in the body is the value. Functions are ordinary values, so a function can return 1. Adder takes an n and hands back a brand new function that adds n to whatever you give it. We make add 5, call it with 10, and get 15. That inner function remembered the n it was born with. That is a closure, and it is the thing we drew as a lantern earlier. It is also, quietly, how you build almost every abstraction in this language. Lists are the workhorse. Here are 8 numbers. Length counts them. Filter keeps the ones matching a predicate, the even ones. And apply takes a function and a list and calls the function with the whole list as its arguments. So, apply plus adds them all up to 31. Small composable pieces that you snap together rather than a method for every occasion. When a list stops being the right shape, you define a record type, a constructor, a predicate, and an accessor per field. Here's a point with an x and a y. Print it and you get a readable tagged value. Pull the x out and you get 3. This is R7RS's structs, and it is all the object system a great deal of code ever needs. And when you want a dictionary, there's a hash table. Set a key, update it in place with a function, note the exclamation mark, which by convention marks anything that mutates, and read it back with a default in case the key isn't there. 42. The bang suffix is a small courtesy the language pays you. Mutation is always visible at the call site. Scheme has no for loop, and doesn't miss it. This is a named let, it binds I and an accumulator, and loop is a function you can call again with new values. Each time round we push I squared onto the front of the list. When I hits 5 we reverse and we're done. 0, 1, 4, 9, 16. It reads like a loop and behaves like one. And here is why that works. This function calls itself a million times. In most languages that is a stack overflow. In Scheme, when a call is the very last thing a function does, the implementation is required to reuse the current frame instead of stacking a new one. So a million deep costs exactly as much stack as 1 deep. Recursion isn't a clever trick here. It is the loop. Then there is the one Scheme is famous for. Call with current continuation hands your function an escape hatch, k. Call k with a value and the whole surrounding computation is abandoned, and that value is returned instead. So the +1 never happens, and the answer is 42, not 43. That is an early return, and generators, exceptions, and backtracking are all the same mechanism, used with more nerve. Errors work the way you'd expect, with a shape you may not have seen. Guard wraps an expression, catches whatever is raised, and lets you match on it. Here we catch everything and pull the message out. Caught, boom, raise, guard, dynamic wind. The whole R7RS error vocabulary is here, and all of it is built on the continuations we just met. The prompt is for exploring. Real programs live in files. Here's one, square, a sum of squares built out of map and apply, and a couple of lines to print the answer. Hand the file to Kaappi, and it runs. 385. No project scaffolding, no build configuration, no main function to declare. A file of expressions is a program. Before you run something, you can just check it. Here I've left a parenthesis off the end. Kaappi check parses the file without executing it and tells you where it went wrong. Line 2, unexpected end of input, and exits non-zero, so it drops straight into a Git hook or a CI job. This is the same engine that powers the squiggles in your editor, which we'll see in a few minutes. And here is the part that surprises people. Kaappi compile sends your program through LLVM. You can see it drop the intermediate LLVM file on the way past. That is not a mockup. That is a real optimizing compiler backend doing its job. And out the other end comes an executable. Run it directly. No Kaappi in front, no interpreter anywhere in sight, just a program. Ask the operating system what it is, and it's a native macOS binary for this machine's own architecture. Scheme compiled to the metal in about a second. One caveat worth knowing before you go and try it, compile handles programs written in core Scheme. The moment you import a third-party package, there's a different route, called bundling, and the ecosystem episodes cover it. One last thing came along in that same one-line install. Thotum is Kaappi's package manager. Thotum is TOML for garden, and it fetches libraries from the ecosystem. JSON, CSV, HTTP, SQLite, a test framework, a web framework, about 20 of them. Watch what it prints. It clones the repository, resolves it to one exact commit, and records that commit in a log file. So a build you make today is a build you can make again next year, byte for byte. And then you just import it. Read a JSON string, pull 2 fields out, print them. That library was 3 seconds of installing and 1 import line, no manifest to write, no virtual environment, no build step. It is worth knowing that a program which imports a package takes a different route to a binary. Kaappi Compile handles core scheme, and for anything with dependencies, you bundle instead. It will tell you so if you forget. So, that's the terminal half. A prompt for thinking, files for programs, a checker for mistakes, a compiler for shipping, and a package manager for everything you'd rather not write yourself. Which leaves the place most of us actually spend the day, the editor. Most of us don't live at a prompt, we live in an editor, so let's finish there. This is VS Codium with the Kaappi extension installed, and underneath it, Kaappi LSP, a language server that ships in the same box as the interpreter. Syntax highlighting, completion, go to definition, and the one that actually changes how it feels, diagnostics as you type. The traditional first program. And notice what isn't here. No project file, no manifest, no build configuration, no main function to declare, no folder structure the tool insists on. One file with 2 expressions in it is a complete Kaappi program. The terminal sits right under the editor, so the loop is as tight as it gets. Save, run, read. Hello world. That's the whole development cycle. And for a surprising amount of real work, it never needs to get more complicated than this. Now, let me break it on purpose. The way you actually break Lisp. Leave a parenthesis off. Watch the end of that line. I haven't saved, I haven't run anything, I haven't asked for a build. There's the squiggle. Unexpected end of input. And here's the part worth knowing. That message is not the editor guessing. It comes from copy check, the same parser the command line uses, and the same one your CI would run. The red line in your editor and the failure in your build are quite literally the same sentence from the same program. Close the paren, and it clears. No save required, no rebuild, no watcher to configure. The server reparses on every keystroke and pushes an empty list of problems the moment there aren't any. If you've ever waited on a compile just to find out you typoed, this is the thing you'll notice first. And it runs. Hello world, and 42. That's the editor setup and the feedback loop closed. So let's write something with a bit more to it. Let's write something small but real. A couple of statistics over a list of numbers. It's a good example because it exercises the 3 things you'll reach for constantly: a helper function, a higher order function, and a local binding. And because the answer it gives is more interesting than you'd expect. Mean is the whole definition in one line. Apply takes a function and a list and calls the function with the entire list as its arguments. So apply plus adds them all up, and we divide by how many there were. No loop, no accumulator, no index variable. You wrote down what a mean is, and that turned out to be the program. Variance is the interesting one. Let binds m to the mean once, so we don't recompute it for every element. Then map runs an anonymous function over the list, subtract the mean, square the result, and we sum those and divide. Read it inside out, and it is exactly the definition from the textbook. And that lambda is the closure we drew as a lantern in the history. It uses m, which isn't its own parameter, and isn't a global. It captured m from the lit it was written inside, and it carries that binding with it into map, which knows nothing about any of this. That capture is what lets you write a one-line anonymous function, instead of a class with a field in it. 7 readings to run it over, and a couple of lines to print the answers. Display writes a value, new line moves on. Scheme keeps those 2 separate rather than bundling them, which is mildly annoying for about a day, and then stops mattering. And look at what comes back. Not 14.142, 99/7. The mean of 7 whole numbers is a fraction, so Kaappi gives you the fraction, exactly, with nothing rounded away. Variance likewise. 244/49. No floating point has entered this program at any point. When you do want a decimal, you ask for one, and the function that does it is honestly named exact to inexact. It doesn't say convert, or to float, or format. It says you are leaving exact arithmetic and entering approximation. That naming is the whole design philosophy in one identifier. 14.142 and change. Both numbers side by side. The exact one you can keep computing with, and the approximate one you put in a report. You chose which. The language didn't quietly choose for you. That's 30 lines of a real program, so let's ship it. Here's the finished program, about a dozen lines of actual code. Now, what does it take to give this to somebody who doesn't have Kaappi installed? In most interpreted languages, the honest answer is a runtime, a package manifest, and a paragraph of instructions. First, check it. This parses the whole file without running any of it and reports what it finds. The same engine behind the squiggles we saw a minute ago. No issues found. It exits non-zero when there is a problem, so this line drops straight into a Git hook or a CI job with nothing else around it. Run it interpreted once more, so we've got the answers on screen to compare against. 99/7, 244/49, and 14.142. Remember those 3 lines. Now compile it. And watch the first line it prints. It drops an LLVM intermediate file on the way past. That's not a metaphor, and it's not a wrapper script. Your scheme is being lowered to LLVM's intermediate representation and handed to the same optimizing backend that compiles C and Rust. A second or so later, compiled. And there it is. No Kaappi in front of it. Same 3 lines, character for character, including the exact fractions, because the numeric tower came along for the ride. This is a program now, not a script that needs an interpreter to be somewhere on the path. Ask the operating system what it is, and it's a native macOS executable for this machine's own architecture. A couple of megabytes, self-contained, copy it anywhere that runs this kind of chip, and it works. One honest caveat: compiled covers programs written in core scheme. The moment you import a third-party package, there's a different route called bundling, and the ecosystem episodes on this channel walk through it. So look at the whole folder. One scheme file, one binary. No lock file, no virtual environment, no node modules, no container to make it reproducible. You wrote a file, and you produced a program, and everything in between was 2 commands you could remember without looking up. And that's the round trip. An idea, a dozen lines that look like the definition of the thing they compute. Live diagnostics while you type them, and a native binary at the end. Same source, 2 ways to run it, and you pick which one you need on the day. So that's the whole shape of it, in one sitting. Where the language came from, and why it looks the way it does. Where it lives on the web, and how to try it without installing anything. One line to put it on your machine. A prompt for thinking out loud, files for real programs, an editor that tells you about mistakes while you type, and a compiler that turns the whole thing into a binary you can hand to somebody. If you take one thing away, make it this. Go and open the playground and change one line of somebody else's code. Not a tutorial, not a course, one line. That is the shortest distance between watching a video about a language and actually knowing something about it. After that, the tour is 12 short lessons, and the 3 seasons on this channel go from your first program right through to shipping a web application. And about the brackets. Everybody bounces off them at first, and then something happens somewhere in the first week. You stop seeing punctuation and start seeing structure. Your editor matches them, your formatter arranges them, and the shape of the code turns out to be the shape of the thing it computes. Nobody who got past that week has ever told me they wanted the semicolons back. It's a small language built by people who care about it. It is genuinely fun to write, and it is sitting right there behind one line in your terminal. Everything you've seen is linked below. Thanks for giving this half an hour. Now go and brew something. Thanks for watching. Subscribe for more Kaappi.